Good evening and welcome to another episode of the EddycurrentDOTcom podcast. You may have seen this magnetic field viewing film before. It's very thin. It's about the thickness of a sheet of paper. There's oil within the film. And there's little tiny nanoparticles. I guess they're nano, they're small. Very small ferromagnetic particles suspended in the oil in this sheet of film. And the whole point is so you can use this with magnetic particle testing when you're playing around with yolks or whatever. And if you put something that's magnetic up to it, it will show you where the magnetic field is and the shape of the field. So you've seen the iron particles sprinkled on, a piece of metal, and you apply a yoke and you can see the flux lines. But this just shows you, so there's the north and the south pole coming out of just some little neodymium magnets connected together. Obviously, so you got a north on the one end and a south on the other. Now what I have here, of course, is the tube. You've probably seen a magnet drop through a tube. I just want to show you two things. Now, first of all, I got one of these fastener plates here, and this one's pretty thick. There's no way I'm going to do conventional eddy current through that because it's just too darn thick. So while I figure out what I'm going to do with this plate of rivets, check out the sliding probe and look at the size of those coils. Those are wide coils. Not only are they wide coils, but they are being energized at 2 kilohertz. So if any eddy current coil was going to be penetrating, this would be the one. Now, you're probably aware that low current is involved with eddy current testing. It's on the scale of milliamps, I guess. I'm not an electrical engineer. Low voltage and low current. But you would think that if it's generating an alternating magnetic field to generate the eddy currents, you would think that the magnetic field would be pretty darn strong, right? Well, if it was, you would certainly think it would register. So the reason I've got the MIS 28 here is just to show you that it is a live probe. There's no sort of calibration here. But it's just to show you that the probe's actually live, right? And I'm going to take it straight up here and hold it up against my film. I'm touching the film, and you don't see any action. So that's just evidence that you don't need a lot of magnetic field, to generate eddy currents and to have an effective test. So now that we've seen that it doesn't take much, I just wanted to take these magnets and drop them through this tube. And the reason for these wires on here, I just wanted to show you what the width of the tube is. And I haven't tried this yet, so I'm not sure how it's going to turn out, but we're just going to see how far the magnetic field from these neodymium magnets goes beyond the tube wall, if it even does. I'm just going to give it a little drop, see, and we'll see what happens. 1, 2, 3. So here's another little lesson buried in here. That there's 3 different types of magnetism, right? So there's ferromagnetic, which is what carbon steel is, and magnetic materials have hysteresis loops. And when you have hysteresis loops, that means you have hysteresis. You retain some magnetic properties after an external magnetizing force has been removed. So if you want to make a permanent magnet, you got to start with a low permeability ferromagnetic material. When it's low ferromagnetic material, it means it takes a lot of external magnetizing force to sort of align all those magnetic domains. We've all seen hysteresis loops, and they're always a nice, smooth, kind of the S-shaped thing, nice and smooth. That's not really how magnetic domains get aligned. They just don't smooth. It's not like that. It takes physical work to move those domains because domains are like little pieces of real estate. And they're randomly oriented in a material just to sort of have equilibrium. One shifted this way, the other one shifted that way. But to get them to move, they don't want to move. They tend to stay in a position where they're neither attracting or repelling their neighbors. So when you apply an external magnetizing force, you're applying a voltage or an EMF. You can think of EMF as an electron moving force because voltage is what makes electrons move. And if electrons are flowing in that direction, electricity is flowing in that direction. Who knows why, but that's the way it is, I'm told. But when the external magnetizing force is forcing those little pieces of magnetic real estate to shift from one position to another and then to start to align, they make noise, and that's Barkhausen noise, and that is actually a type of non-destructive test. I just wanted to say a few things about the other 2 types of magnetisms. You got ferromagnetism, related to magnets, and then you have paramagnetic material. Well, Paramagnetic materials like aluminum are affected by magnets. Here's the difference. Ferromagnetic materials have a permeability number that's B over H, quite a bit larger than 1. Could be 50, could be 500, could be 20,000. But when you've got some number that's quite a ways above 1, that's going to be a ferromagnetic material. Paramagnetic materials have a permeability value of like 1 point something. Diamagnetic materials have a permeability number of slightly less than 1. That's about the extent that I ever see diamagnetic and paramagnetic explained in literature. And that's unfortunate because there's more to it. Paramagnetic materials are attracted to magnets. The only difference is when you take the external magnetizing force away, paramagnetic materials do not retain any magnetic properties. They have no hysteresis loops. And diamagnetic materials, on the other hand, are repelled by a magnet. And similar to paramagnetic materials, they do not retain any hysteresis after you remove the external magnetizing force. Now, if you go to the EddycurrentDOTcom YouTube channel, in the playlist under the Action Lab, there's a great video of the scientist on there attracting paramagnetic materials to a magnet and repelling diamagnetic materials with a magnet. So that's kind of cool. So if you just kind of visualize all that, and if you watch that video, you'll never forget the difference between ferromagnetic, paramagnetic, and diamagnetic. Now, anything that's got a permeability value right around 1, we just say that they're non-magnetic. When we can treat them as non-magnetic, it makes a lot of our calculations easier because we just use the number 1 in the calculation. So, all right, if you disagree with any of that, just leave a comment down below. But I hope this video is a little bit educating, maybe mildly entertaining. But that's all I got tonight.